All right, I'm picking up where we left off here. We're going to talk about the physical properties of matter, but also how things phase change or change states of matter. So the two main factors that you're going to be focusing on when you're talking about phase changes is the amount of kinetic energy that particles have and the strength that the attractions feel for one another, which are your IMFs, mainly for doing phase changes. However, if we're talking about chemical changes, we're breaking bonds. We're breaking ionic bonds or covalent bonds. However, you can still talk about the IMFs present too. A couple of other words you're going to be seeing a lot are degrees of freedom. So different phases have different movements of particles. Translational freedom means that these particles can move from position to position. That's only going to occur in gases because they're the only ones free to move around in space. Liquids stay next to one another in contact with one another, which means that they don't feel the volume of their container. Rotational and vibrational freedoms are related to the ability of one particle to move itself, not move position, but move itself in an axis. Rotational is talking about reorienting its direction. That's only going to happen with liquids and gases because they're not locked in position. Liquids just feel more attraction for their neighboring particles, which means they stay in their liquid state. Vibrational freedom is what you see whenever you look on some of the simulations you actually did last unit. And the vibrational freedom is talking about the particular atom having the pent-up energy, chemical energy, that's now being conveyed as a vibration. It can put off a series of waves that we can then measure with an X-ray, and then we can track how a lattice actually looks based on these the spectra that we develop from these. These are called IR spectra. We're going to talk about these at the end of this unit. Another thing we're going to talk about is X-ray crystallography, and that's how we can actually depict different chemical arrangements in lattices. All right, and we're going to save that for tomorrow. All right, so this is the first part of your reading guide, and I wanted you to define these different physical properties and then relate it to intermolecular forces. You can pause this and copy down what you want to. I'm going to hit the highlights. So freezing point, we all know, is the conversion between a liquid and a solid. The IMFs part is the harder part to think about. So what I like to do is I like to say, okay, well, freezing point is just the opposite of melting point. Melting is going from solid to liquid. Freezing is going from liquid to solid. So you can see right here on this bottom portion, as opposed to going from the liquid to solid state, if I have a high melting point, that means that I refuse to go from solid to liquid. I have a great force of attraction for my neighbors, meaning I have high intermolecular forces, maybe dipole-dipole, maybe high amounts of London dispersion or strong hydrogen bonds. So if I have a high melting point, that means I'm going to have high forces. Since melting point and freezing point are technically the same point, same temperature at a constant pressure, then if I have a high freezing point, that also means I have great attractive forces. It's kind of weird to think about that way, but it's the best. Surface tension is the ability to resist increasing surface area. So water particles, whenever they are free to move around, they always bead up into a sphere. So that's the answer to this bottom question. Given the same volume, which geometric shape has the least amount of surface area? That would be a sphere. That's why water particles form droplets, because they have that cohesive nature about them as well, so they want to stick together, limiting the amount of surface, which increases the attraction they feel for one another even more. However, this one last point here is important, because if you have a low surface tension, that means that you are going to vaporize easily. So if you have, let's say, a layer of water, and your H2O particles are sitting at the top, they only have a neighbor on their left and their right that are going to attract them. However, the ones on the inside of the water column itself, they have neighbors top, bottom, left, and right that are able to attract them. So the underlayer is stable, while the upper layer, where the surface is, are less stable. That means that they have the potential to leave the surface. They have high potential energy. And when they leave the surface, they go from liquid to gas, and that's what we call vaporization. So high surface tension limits the amount of vaporization. Low surface tension increases the amount of vaporization. Capillary action is another phenomenon we've experienced in water. It can happen in other liquids as well. The two highlighted words, adhesive and cohesive, are words I'm expecting you to know. Cohesive means they stick together, they cooperate together. I'm using water as my example again. So water and water sticks to each other with hydrogen bonding. Adhesive means they stick to the sides of their container or adhere to something else, not themselves. And capillary action is talking about the force against gravity, and that means that it's got a higher attraction for whatever it's stuck to or itself versus the pull that gravity has on matter. And if we're talking about greater capillary action, that means it's going to move up a small capillary like the xylem of a plant. More so if it has high capillary action or stronger IMFs. That's because it has the ability to creep up the sides of a container due to the attraction it feels for the container, aka adhesion. One note here, water, when it creeps up the sides of a container, makes a nice meniscus that has this shape here. And if you're talking about something not so polar, like mercury, it forms like a bubble. It does not form that nice loop meniscus. So mercury is an example of not very good capillary action, not strong forces. The last of these are viscosity, heat of vaporization, and vapor pressure. Viscosity is talking about how viscous something is, and it's viscous means resisting flow. So if you have a strong attraction for your neighbor, you don't flow very well. Lack of flow means you have high viscosity. So if you are thinking about ketchup, honey, molasses, mayonnaise, these things have high viscosity. Water does not. Let's say sugar-free maple syrup does not have a high viscosity. They flow very well. Another thing to consider, not IMFs, is the complexity or the length of a molecule. So if we're talking about C2H6 versus C12HO, let's say 26, these particles, these hydrocarbon chains are really long when you keep adding these carbons, and so they can get entangled, which limits the amount of flow. And that's why molasses and syrups, which are mainly carbohydrates, which are hydrocarbons, have a high viscosity because they don't flow very well. One other note here is that thermal energy can allow for viscosity, natural viscosity, to be overcome because it limits the amount of interactions they have with one another because particles are moving faster. Heat of vaporization, VAP means to convert from liquid to gas. That's what vaporization is. Don't forget the definition is talking about 1 mole. If you have a high intermolecular force with your neighbor, it takes a lot more energy to overcome the attractions that you feel for one another, directly related. Vapor pressure, I briefly talked about this. I'm going to start at the bottom right here. If you have a strong IMF, that means that you are non-volatile. You don't vaporize easily. If you don't vaporize easily, then you don't have any pressure. So if you're not creating pressure, then you have a low vapor pressure. So thinking about water does not vaporize very easily. So if it doesn't vaporize very easily, it's not creating vapors, therefore it's got nothing hitting the sides of its container, which means that it's not causing pressure. Water has hydrogen bonding going on, which limits the amount of vaporization, limits the vapor pressure. So this one's indirectly related. Strong IMFs yields low vapor pressure. The related component here is boiling point. So boiling point is the ability to turn liquid into vapor, but you're adding temperature to do this. You're increasing the temperature of the substance. And if you have strong IMFs, then you have to heat it up to a higher temperature, aka higher boiling point. This is vapor pressure in detail. So I've talked about some of this. Take a minute and read through what you need to. We've already talked about equilibrium vapor pressure way back before midterms. So this is a quick review. Vapor pressure can only be measured when you have a closed container, because otherwise the vapors would leave and they would not create the pressure that you're looking for. So if you're talking about vaporization, you're talking about a rate of the forward reaction going from liquid to gas. Well, gas can also deposit or condense into liquid. So the rate of the forward reaction is going to then eventually equal the rate of the condensation or the reverse reaction. And once this point is hit, we call that dynamic equilibrium. There's no net change overall in the concentration of the vapor present or the liquid present. The equilibrium vapor pressure is the vapor pressure that we speak of when we say quote-unquote vapor pressure. Back to the word volatility. High volatility means that you don't have very good intermolecular forces, so you can create that vapor really easily. And I have a couple of pictures here for you. Products, or picture A is showing the vaporization process, picture B is showing the condensation process. Eventually, though, we get to the point where our rates of evaporation and condensation are going to be equal, which is the time that vapor pressure is attained or measured. Usually, if you were talking about the relationship between pressure and temperature, it is a direct relationship, and that is because these vapors form quite easily when they have more kinetic energy. More kinetic energy comes from increasing temperature, and it can overcome any attractions that they have for one another, aka their IMFs. I keep saying the same thing over and over again. I don't know if you've heard this, but it's all related to physical properties, so I'm trying to explain them in different ways. Vapor pressure and boiling point. If you're trying to look at this graph, you'll notice that water has a boiling point at 100, at 760 torr, which is 760 millimeters of mercury, which is 1 atmosphere. That's our normal boiling point. Other substances have lower boiling points, meaning they have less IMFs. So we've used this equation before back when we did a vapor pressure lab. I just want to let you know that it is available to you on the AP exam. They can ask you to determine the pressure of two different vapor pressure of one substance at two different conditions, given all the available information. So I'm going to scroll back up, but the word distillation to you should mean boiling off a mixture of liquids at different boiling points. So the blue question right here, which of the following would be removed in distillation first? Who's going to be distilled first? Who's going to be removed first? When you look at the temperatures, you see diethyl ether is about at 35 degrees C. It should be removed first, leaving you with the ethanol and the water for later. So you can catch these different vapors after that you've met its boiling point and separate a liquid mixture in this manner. One more depiction, this is from your textbook. The vapor pressure of a liquid can be measured easily using a barometer. You can see the three liquids here: ethanol, diethyl ether, water, and you can compare them based on the amount of pressure that they are causing in the barometer. Remember that the air pressure is pushing on the mercury, and the mercury is traveling up the tube. If something has a very low pressure, then the substance is able to, the substance does not cause that much pressure back on the air. We'll come back to that one. If the liquid diethyl ether was placed in a container and allowed to come to dynamic equilibrium, what would happen if the volume of the closed container was increased? So remember, vapor pressure is measured at equilibrium. So if you change conditions at equilibrium, you're implementing Le Chatelier's principle. So this is also a review question. Le Chat says, whenever you, let's see what do you do here, the volume of the container was increased, then you're going to go to the side with more gas. So you're going to shift to the vapor state and decrease the amount of liquid present in the solution. Opposite for the next question. Part 2 of the reading guide.